So, hello everyone. My name is Sohil, and for my project, I decided to go with a Norwegian sepsis patient data set. So, the data consists of more than 100,000 sepsis patients from the Norwegian Patient Registry and Statistics Norway. And it was obtained from this study, which is publicly available, and the data is fully available to download in the associated study. The target variable for this would be the mortality. That's what I wanted to predict. So whether the patient would live or wouldn't live. So, for example, the outcome would be one for a deceased or zero for living. And because we want to predict this, and it's a binary feature, this is a classification problem. So the predictor features for this target includes the patient's age, their sex, the length of their hospital stay, and their sepsis episode number. So already we can see three theoretically numeric features, and then sex would be a categorical one. The data also includes ICD codes, which essentially correspond to any underlying diseases or conditions the patient might have. So, for example, it would include these codes right here, which would specify specific conditions or diseases that are known to medical literature. However, it's in a very unstructured format and isn't friendly for any learner algorithms. So we do have to encode this somehow to make it usable. And we also have another problem is that there is an overrepresentation of uh, living patients over dead ones. So this is a class imbalance issue. So we have to address those two issues. So to do that, we first one-hot encode the ICD values. So we take all possible ICD values from the data, and then we create a new column for each. And each column would be a binary one. So the patient would have that or not, one or zero. And then we would also check for any missing values. And to fix a class or representation problem that I mentioned earlier, I randomly sampled only a subset of the living patients so that there's an equal proportion of living patients to dead ones. Additionally, I log transformed the hospital stay variable as that seemed to benefit the most from a simple log transform, and because that was one of the most heavily skewed distributions of any feature in the data. After splitting the data into a training and test set, I impute the outliers by detecting via a z-score threshold, and then imputing them with a custom function for a median. So I wrote a bunch of custom functions for outlier imputations and also for normalization and standardization, which we'll use later right before logistic regression and neural networks. And these are the algorithms I chose to classify the data. Random forest I chose because it is known for being a very good classifier. It's very robust, and it's a lot better than Bayes decision trees if used correctly, as is a bagging method for that. And then I included a Bayes decision tree using RPart. Just out of curiosity, though, if this doesn't perform as well as random forest, there would be no point in including this since I already have random forest. I also included logistic regression because it can be a good primary feature with proper feature engineering. The issue, however, is that because of our one-hot encoding, it leads to something called dummy variable trap. That could lead to issues with multicollinearity in the data. And logistic regression doesn't like that at all. So for this project, I used the cv.glmnet and alpha equals 1 parameter. So that basically includes a lasso aspect to the logistic regression model, and that would account for any multicollinearity in the data. And for neural net, I only included neural network just out of pure curiosity. I wouldn't choose this I wouldn't have this as my first choice in a classification scenario, and I'm not sure about it if it would be appropriate in real world classification scenarios. But I want to see if it would work just as well for a classification task if tuned properly. So I'm going to go ahead and run all of that in this formatted RMD file. So we have it follows the CRISP DM structure pretty well. We have data acquisition and exploratory functions, pre-holdout preparation, post-holdout preparation, data correlation and distribution plotting, and then also we have our models as well with their individual parameters that we can control for. And then we also have our ensemble at the end, which I will go over in a moment. So I'll go ahead and run all of this. So as you can see, we have our PDF file here with the results. So I'll go ahead and open that. And here we have a summary of our process following a CRISP DM model. We have our distribution and correlation plot of the raw data. And then we have our model metrics. So for each model, I calculated these metrics since it was a classification task and paid close attention to the precision, accuracy, and K-fold and AUC. Those were the four ones that I really paid special attention to. But also other ones are very good for a general look at how well the model fits. So as you can see, they all seem to have similar metrics, though notably decision trees has lower performance across the board. And it has high sensitivity, and because of its lower performance, I would not use this in an ensemble. For the rest, they seem pretty good overall, though I believe I could have found them tuned a lot better with sampling data sets and then trying out different hyperparameters and automating the process. So bootstrapping, for example, would have been a good way to tune it even better. But yeah, I was also surprised to see neural networks having good performance. So that is very interesting to see. So again, like I mentioned, decision trees had the lowest performance, so we dropped that from the ensemble. And honestly, it was a bit difficult to get some of these models, especially logistic regression and neural networks in order for us to work properly with this data, mainly because there are in-depth issues that occur. So for example, neural networks, I had convergence issues. So in order to solve that, I had to tune the thresholds and the max number of steps to a value where the neural network wouldn't fail to converge. And then for random forest, playing around with the number of trees, and then also for logistic regression, choosing to do lasso instead of classic logistic regression was a good choice. For the model fits, as we saw with the metrics, we paid close attention to accuracy, precision, AUC, and K-fold. So for all the models, they all performed pretty similarly, though decision trees was on the lower side, as we mentioned. And now we're going to go ahead and go over ensemble, which includes the random forest, logistic regression, and the neural network model that we trained on the training data set. So To construct the ensemble, what I did was I created a custom ensemble function that essentially uh, held all of the previous models that we trained, and uh, for each patient, it classifies using the majority vote of the ensemble. So we validate our ensemble using these metrics. Um, However, we don't use AUC and K-fold mainly because of the ensemble nature. We assume redundancy and reliability, and also because we can't extract the exact class probabilities from the ensemble itself as compared to individual models. We cannot get the ROC curve, and as such, we can't get the AUC. Uh, and then the general summary here. This shows our entire process from the data engineering to the modeling, the validation, and then to choosing the models for the ensemble, and then using the ensemble to predict or classify new data. And in order to do that, I generated sample patient data for this project and attempted to classify it as either deceased or living. So if I go here, the ensemble, we see our metrics. The ensemble performs pretty well, pretty on standard with the other models. So there isn't a huge performance improvement over a single model for the ensemble, though. Uh, uh, though because of the ensemble nature, redundancy and reliability is assumed to be better. And then this is the new sample data that I generated. And for each patient, the ensemble classified it as living or deceased. And just to reference again, this is the study that I received the data set from. So again, it's fully available for access, and the associated attached data set is fully available for anyone to download.